Let's start with the idea of kinetic energy. Which is all about the energy associated with motion. If you've got an object that's moving, it has energy because it's in motion. And this energy is really the same type of thing ultimately as the thermal energy and bond energy we've been looking at earlier. In the past, it was thought that these were different things. You've got the heat associated with changes in temperature, changes in phase. And then you've got the mechanical energy of movement of an object. But over the last 200 or 300 years, it was discovered that these are actually the same sort of thing. The changes in temperature, changes in phase are really the same energy as energy of motion. It's just a different kind of energy, but it's still measured in joules. They're still interchangeable. Kinetic energy in particular, like let's say you've got an object that's not moving and you want to make it start moving. What do you have to do to the object to make it start moving? Like let's say you've just got a cart and right now it's not moving. Yeah, you got to apply a force, right? You apply a force to it. A force, let's say to the right. You push on it and it's going to start moving. And if you continue pushing, it gets faster and faster and faster. And you're applying a force as it moves some distance. Even if you just give it a little tap, it starts moving while you're applying the force. So that force you're applying times the distance traveled, what do we call that if you're applying a force to a moving object? Yeah, that's work. You're doing work because you're applying a force as the object moves some distance. So you're doing work as you push on the object. And we can actually apply an idea about work that you're actually going to see later on in 7b, but let's go ahead and introduce this now. In general, if you apply a force to an object, you cause its velocity to change. You're not just giving it a velocity, you're causing a change in velocity as time passes. And we call that change in velocity as time passes acceleration. You apply a force, you make the object accelerate. You make it get faster and faster and faster, or slower and slower and slower if you're applying a force opposite to the direction it's moving. Like if the object's moving this way and you push this way, you're going to make it slow down. That still counts as an acceleration. It's just acceleration in the negative direction. And these should be proportional. You apply 3 times as much force, you get 3 times as fast of an acceleration, which means force should equal something times acceleration. What would you expect that something to be? What is that multiplier, that coefficient? It's not just distance, because the difficulty isn't how much it's accelerating and how far it travels. Yeah, it's going to be mass. The more massive the object is, the more difficult it is to make it accelerate. Like if you've got 2 objects that are different masses and you want them both to accelerate the same rate, getting faster at the same rate, it's going to take more effort to get the more massive one to accelerate at the same rate. Or to put it another way, you apply the same force to both objects. The less massive one is going to accelerate very quickly. The more massive one accelerates more slowly. So mass is the constant of proportionality here. The force applied to the object, and this should really be the net force, the total of all the forces acting on the object, equals the mass of the object times the acceleration, how fast its velocity is changing. This is usually called Newton's second law. Newton's first law isn't really all that different. Newton's first law just says if there's no force, then there's no acceleration. But this is a more powerful idea, the idea that if there is a force, then the object accelerates. It changes how fast it's moving. And the acceleration is proportional to the force, with mass as the coefficient of proportionality, the proportionality constant. And from this, we can get some more information. One thing we can figure out is the units of measurement, which is a very useful tool to have. If we take a look at the units here, first of all, what is mass measured in? Yeah, mass is going to be measured in kilograms. And what about acceleration? What are our usual units for acceleration? Meters per second is velocity. That's how fast the object is moving. Because velocity is distance over time. How far the object moves every second. So velocity, how fast the object is moving, is measured in meters per second. But acceleration isn't how far it travels per second. Acceleration is how much the velocity changes per second. Acceleration means you're changing how fast you're moving. And specifically, acceleration is how fast your speed is changing. Velocity is measured in meters per second. Time, again, is going to be measured in seconds. So what do you get if you take meters per second and divide by seconds again? The meters don't cancel out because this seconds is in the, or the seconds don't cancel out. This seconds is in the denominator. This seconds is also in the denominator. So yeah, those are going to combine. Meters per second divided by seconds is the same as multiplying by 1/seconds. So these seconds combine. We end up with meters per second squared. And you may have seen this in, for instance, g, the acceleration of gravity, 9.8 meters per second squared. That's describing how fast, not just how fast the object falls, but how fast its speed is increasing as it falls, how fast it's getting faster as it falls. So that's what acceleration is. Velocity is how far you travel per second. That is how much your position changes per second. Acceleration is how much your speed changes per second, how quickly you're getting faster or slower. So that'll be measured in meters per second squared, which means force is measured in kilograms times meters per second squared. And we call that newtons. Newtons, capital N, is kilograms times meters over second squared. So that's the standard units of measurement we're going to use for newtons, or for force. Force is measured in newtons, and 1 newton means 1 kilogram meter per second squared. Any questions on the relationship there so far? So let's fill in some values here. Now that we know force is measured in newtons, and what's distance measured in? If you're just talking about how far an object has traveled, yeah, that's just measured in meters. And work is a transfer of energy. What do we measure energy in? Yeah, energy is measured in joules. So this provides another way that these quantities are related. Joules is the same thing as newtons times meters. By the way, the usual convention for capitalization, if a unit of measurement is named after somebody, the abbreviation gets capitalized, but the name itself does not. So newtons is written in lowercase, but the N is written as a capital N. So if joules is the same as newtons times meters, we can also rewrite newtons as kilogram meters per second squared. Newtons is really just an abbreviation in the first place. Newtons is shorthand for kilogram meters per second squared because we don't want to have to write that out every time. If we did though, we could say joules is kilogram meter per second squared, that's newtons written out in full, times meters again. And this time the meters are going to come because they're both in the numerator. So what do we get if we combine those? Meters times meters is remember, this is meters over 1. Yeah, they're both in the numerator, so they're going to combine to meters squared. If they're both in the numerator or both in the denominator, they combine. If you got one in the numerator and one in the denominator, they would cancel out. But this is another way of writing joules. Joules can be written as newtons times meters if you want to compare it to some forces. Joules can also be written as kilograms times meters squared over seconds squared. So you are always free to make these substitutions. Anytime you see joules, you can replace it with newtons times meters, or you can replace it with kilogram meters squared per second squared. And that also works in reverse. Anytime you see kilogram meters squared per second squared, you can replace it with joules. Anytime you see kilogram meters per second squared without the squared on the meters, you can replace that with newtons. Same thing, just a different way of writing it. So those can be some very useful substitutions to get units to work out right and figure out what the units of the result should be. Any questions on that so far? So now that we've got the units here, let's try exploring this idea of work equaling force times distance a little more. Work is force times distance. And we know that force, assuming that this is the only force acting on the object, the force can be rewritten as mass times acceleration. So let's try making that substitution. We know force can be written as mass times acceleration. So the work you're applying to the object to make it go faster is the mass of the object times how quickly it's getting faster, acceleration, times how far it travels. But we can also replace acceleration with its definition. Acceleration is just how fast the speed is changing, delta v over delta t. Mass times delta v over delta t times distance. So the work you're doing is the mass of the object times how fast the velocity is changing times how far the object travels. Any questions on that so far? And at this bit, we can do a very clever bit of algebraic wizardry. If we regroup these terms a little bit, because we've got change in speed times change in position, all divided by change in time. If we regroup a little bit and put these together, what do we call distance over time? Yeah, that is velocity. So the distance over time can be replaced with velocity times mass times delta velocity equals the work done. So we've gotten this written entirely in terms of velocity. We don't have to worry about distance. We don't have to worry about time. Everything's written in terms of mass and velocity and change in velocity. The problem is we don't really have one speed to multiply by because this object started off at rest and it's getting faster and faster and faster. So if v is changing, we can't just multiply mass times one single speed times the change in speed. What we can do instead, though, is split it up into a bunch of little pieces. We can say we're adding up the mass of the object times the speed right now times a tiny change in speed. And now we can get into a little bit of calculus. What do we call it in calculus when we're adding up some function times little tiny change? This might look a little more familiar on a graph. If we have a graph, let's say this is the velocity axis and this is some other function. If we've just got some curve and we're multiplying the height of that curve times a tiny change in v, we get the area of this rectangle. If we then take the next value of mv times a tiny change in v, we get this rectangle. The next height of the curve, mv, whatever the function is, yeah, this is ultimately building up to an integral. The whole point of an integral is adding up something times a tiny change over a lot of those tiny changes. The summation of average value times the little change is an approximation, but the integral makes it exact. We take the limit as these pieces get smaller and smaller and smaller. The summation turns into the integral of mv with respect to v. dv basically just means delta v if you're looking at very, very tiny changes. So the work done is integral of mv with respect to v, presumably a definite integral from some initial velocity to some final velocity. And if we actually integrate that, the m is a constant, so we can pull that out. Anyone remember how we would integrate v with respect to v? It might help if you write this as an exponent, v to the first power. Yeah, you just increase the exponent by 1 and divide by the new exponent. So we get v squared over 2. So that's the work. And of course, this really should be from some v initial to v final, because we're talking about a transfer from initial to final. So if we plug those in, we've got, and the m over 2 is a constant, so we can factor that out. We've got v final squared minus v initial squared, because you plug in those endpoints and subtract to find the definite integral. So this would be the amount of work done. If you're pushing on an object to make it get faster, the amount of work you do is half the mass times the difference in speed squared. And we could write that as a delta also. The change in speed squared. And we write the speed squared in parentheses to emphasize that we're squaring both the initial and final values first and then subtracting. So we now have a formula for how much work it takes to change the speed of an object. Any questions on that so far? And work is just a transfer of energy. So that means this quantity, half the mass times the change in speed squared, is some sort of energy we're giving to the object to make it go faster. And what would we call that energy associated with a speed or a change in speed? Exactly, this is kinetic energy. The formula for kinetic energy comes from doing this integral. You start with the idea that work is force times distance and force equals mass times acceleration, and all the rest follows from algebra and calculus. So this isn't just some magic formula pulled out of a hat. This is the inevitable conclusion of the assumption of the definition of work and the definition of force. This automatically leads to the idea that if you want to change an object's speed, this is how much work it costs to do that. So this is where we get the formula for kinetic energy. And we would call that work the change in kinetic energy. Half the mass times the change in squared speed. That is final speed squared minus initial speed squared. It's important to square the speeds first and then subtract to find the difference. Or if you just want to know how much kinetic energy it has right now, usually what we care about is the change. But if you want to know how much kinetic energy does it have right now, you would just take off the delta. Half the mass times the speed right now squared. So that's the formula for how to calculate the kinetic energy of the object. Any questions on that so far? Yeah, this is what kinetic energy is. This is why we have to have this formula. And you can get a lot of this just by looking at the units of measurement also. Like we should expect that the amount of effort it takes to get the object to speed up is going to depend on its mass and is going to depend on its speed. The heavier the object is, the more effort it's going to take to speed it up. And of course, the faster you want it to move, the more energy it's going to take to speed it up. So even if we didn't run through all the calculus, we could probably guess that it's going to have something about mass and something about speed. Mass and speed. But if you just make a guess as a guess for a formula, a good way to check whether that guess even makes any sense is to check the units. Mass is measured in kilograms as usual. Speed is going to be the usual meters per second. Do those units work out to what we want for joules? Is joules kilogram meters per second? What is joules going to expand to if you actually write out joules in terms of the basic units? It's not just kilogram meters per second. What was it? What else do we need here? Yeah, we need meters squared and seconds squared. We can get that by putting a squared on the velocity. So just based on the idea that the more massive the object, the more work it's going to take to speed it up. And of course, the faster you want it to go, the more work it's going to take. Based on that alone, we should expect that kinetic energy is going to depend on mass and velocity. The fact that the units don't work out quite right, we need the squared on the meters and the squared on the seconds, suggests we should square the velocity. So we can get this far just from looking at the units of measurement alone. But what is this formula missing? If we wanted the change in kinetic energy, yes, it would need a delta. But even if we don't want to change, if we just want how much kinetic energy right now, does this match the formula we got earlier? It still needs the 1/2, right? And this is the tricky bit. You can't figure out that 1/2 just from looking at the units of measurement. According to just the units of measurement alone, mv squared should be fine. You get the right units of measurement, kilograms times meters squared over seconds squared. But ultimately, the reason why we need this 1/2 is because it emerges from taking the integral. We were integrating v with respect to v. When you integrate v, you get v squared over 2. So mathematically, that over 2, that 1/2 comes from the integral. Conceptually, you could say that if you're doing work to this object, you're not moving it at speed v the whole time. Some of the time it's going slower than v, some of the time it's going faster than v. So on average, you get a v over 2. So that's one way to interpret that 1/2. But you're not doing all the work at speed v final. You're not doing all the work at speed v initial. You're doing most of the work about halfway between those on average. So that's conceptually where the 1/2 comes in. But mathematically, it's entirely from this integral. Any questions on that kinetic energy idea so far? So that's kinetic energy, and that's specifically what we would call translational kinetic energy, sometimes labeled with a subscript TR. Translational in the sense of moving through space. If you've got an object that's just drifting through space, changing its position as time passes, we would say that its motion is translational motion. But what's another type of motion it could have? Instead of drifting through space, changing its position, how else could an object be moving? Rotational motion. The object could be spinning around its own axis. So that would be rotational motion. And there's also a kinetic energy associated with rotational motion. Like if you've got an object that's not spinning and you want to make it start spinning, you have to do work to make it start spinning. And of course, it could be doing both. Maybe the object is tumbling. Maybe it's rotating as it drifts through space. So it can have translational kinetic energy and rotational kinetic energy at the same time. Or maybe just one or the other. Maybe it's just translating, or maybe it's just rotating, or maybe it's doing both. But the formula for rotational kinetic energy, we're not going to get into this in much detail until we get to 7b, where we'll see more stuff on rotation. But rotational kinetic energy is a very similar structure. Instead of talking about the translational squared, we're going to have a quantity called rotational or angular speed, which is change in angle over change in time. That's the rotational speed, the Greek letter omega. So for instance, if an object is spinning at a certain rate, you'd be measuring this in presumably degrees per second or radians per second or rotations per second, describing how much it spins per second. And it's the same structure. You're going to have that omega, the angular speed, squared, times a quantity over 2. Although in this case, the quantity isn't just mass. It's a quantity called moment of inertia. Moment of inertia is basically a measure of how difficult it is to get an object spinning, or how difficult it is to slow it down or speed it up once it's already spinning. It ends up depending on both the mass of the object and how the mass is distributed. If all the mass is close to the center, it's pretty easy to spin. If the mass is further from the center, it's more difficult. We're going to get into this in a lot more detail towards the end of 7b. But for now, just keep in mind that an object can have kinetic energy because it's moving through space or because it's spinning. Those both count as kinetic energy. It takes work to make an object get faster. It also takes work to make an object spin faster. So those both require transfers of energy. Any questions on that so far? Then let's take a look at potential energy as well. We can get the idea of potential energy from the same concept, the same idea of work being force times distance. So we can start with the core idea once again that work is force times distance. But in this case, let's control the experiment. Let's assume that we're not changing speed. What would be an example where you have to apply a force to an object just to keep it moving at a constant speed? So not speeding up at all, just applying a force to keep it moving at a constant speed. Like if I'm just holding an object, am I applying a force to this right now? Except for one thing. What force is already acting on this, even if I'm not holding it? Yeah, gravity. If I'm not applying a force, it's just going to fall, which means I am applying a force in which direction? How am I preventing this from falling? Yeah, just by virtue of holding this in place, I am applying an upward force. My hand is applying an upward force to prevent the object from falling. In the absence of that force, it's just going to fall. So I'm applying an upward force that's precisely enough to counteract the downward force of gravity. Exactly, it's acting against gravity. So the force I'm applying is the opposite of the force of gravity. I'm applying a force that's exactly opposite to the force of gravity. If I'm holding it still, I'm applying a force to cancel out the force of gravity, so the total force is 0. But even if I'm moving it at a constant speed, I'm still applying exactly enough force to cancel out gravity. Because and this goes back to Newton's first law, no force, no net force is the same as no acceleration. If I want to move the object at a constant speed, no acceleration, just motion at a constant speed, then I need to make sure the total force is 0. So even if I'm moving the object, as long as the speed doesn't change, the force I'm applying is the exact opposite of gravity. Or if you're trying to compress a spring, for instance, you're applying a force that's exactly the opposite of the spring force. Or if you're trying to pull two magnets apart from each other, you're applying a force that's exactly opposite of the magnetic force. Whatever you're doing, as long as you're trying to move an object at a constant speed in the presence of some sort of natural force, the force you're applying must be the exact opposite of the natural force. So I'm just going to write F natural here. The force you're applying has to be the opposite of the natural force, whatever that force might happen to be. Which means if you're talking about the force you're applying, because the work done by you is the force you're applying multiplied by the distance traveled. And we can call that a change in potential energy because we're talking about work. That's a transfer of energy. It can't be kinetic energy because we're assuming we're moving it at a constant speed. Let's say you're just lifting this object at a constant rate. So this work done is a change in potential energy. Potential in the sense that it's sort of a stored energy. It's a capability of doing work. For instance, if you lift up an object, you're investing work in it, and let's say you put it on a shelf. That high up object now has stored energy. How could you get that energy back out of it? If it's up on the shelf, it's in this sort of unstable, high energy situation, right? Yeah, what happens if you drop it? What happens if you knock it off the shelf? What's it going to do? It's going to fall, and as it falls, what happens to it? It's going to increase its velocity, and therefore it's going to gain what kind of energy? Kinetic energy, right? Exactly. The potential energy decreases and the kinetic energy increases. So when you lift up an object, you're doing work to invest energy into it. You're storing energy, and we call that stored energy potential energy. Energy related to its position that is essentially stored work. But that is now in a high energy situation. If you knock it off the shelf and let it fall, that potential energy that was stored in it turns into kinetic energy, meaning it gets faster as it falls. And we can get a formula for how much stored energy based on this idea of force times distance. Assuming you're doing work just to lift up the object or move the object in the force, in the presence of the force, without changing the speed, all the work you do is just changing the stored potential energy. That's equal to the force you're applying. But again, in order to make sure it's moving at a constant speed, the force you're applying has to be the exact opposite of the natural force. So negative F natural times distance traveled. And again, we could think of these deltas, if we're talking about very small changes, we could think of these as D. Actually, let's just leave this one as a delta. We've got a force. And then really the problem with this, as long as the force is constant, this works fine. You can just multiply the constant amount of force times the distance traveled. But if the force is changing, for instance, in this case of a spring, if the spring is at its equilibrium length, there's no force at all. If you compress it a little bit, you get a little bit of force. If you compress it a lot, you get a very strong force. So the force might be changing. So again, we're going to split this up into tiny pieces and multiply the force right now times a tiny bit of distance, plus the force a little bit later times a tiny bit of distance, plus the force a little bit later times a tiny bit of distance. So we are adding up natural force times a little bit of distance. And again, if we look at a bunch of little tiny changes added together, instead of writing it as a summation, what would we write it as? What tool from calculus adds up a whole bunch of tiny changes? Yeah, once again, this is going to be an integral. If we add up a bunch of kind of small changes, this is an approximation. But if we take the limit, as the changes get smaller and smaller, the summation becomes an integral of force, and then delta x would be written as dx. So this is actually our definition of what potential energy means. Presumably it's from some initial position to some final position. But this is actually the definition of potential energy. So you can find potential energy associated with any force as long as it has certain properties, which we're not really going to get into in this class, but basically a force that allows you to store up work, as opposed to a force where work is just sort of lost. The potential energy you're storing up can be calculated based on this integral, as long as you've got some sort of formula for force. Any questions on that so far? This also works in reverse as well. What's the opposite of an integral? Yeah, a derivative. So if we take the derivative of both sides, derivative of potential energy with respect to x, and on the right side, the derivative and integral cancel out, so we just get negative force. You could also think of this as just dividing both sides by delta x, and you get delta PE over delta x. Then we'll take the negative of both sides to cancel that out. So this gives us another way that force and potential energy are related. Force, specifically that natural force we're talking about, like the force of gravity or the force of electrical repulsion or attraction or force of a spring, is equal to the negative derivative of potential energy. And one of the really convenient things about this, later on we're going to be making graphs of energy. If you've got a graph of position versus potential energy, that is some sort of shape, what does the derivative tell you about a graph? It is a rate of change. How does that display on a graph? Like, how can you tell what the derivative is based on the shape of the graph? What do we call that change in energy over change in position? Change in energy over change in position, what would that be called on the graph? That's the slope, exactly. So the slope of the potential energy graph tells you how strong the force is. Like over here, we've got a steep slope. That suggests in that region, there's a strong force. Over here, there's a much less steep slope, so we'd assume that's a weaker force. At the vertex here, the slope is 0. It is at that instant flat, which suggests no force at that instant. And then the negative sign just takes care of direction. If the slope of the graph is positive, that means the force is acting in the negative direction. That is, these force points towards lower potential energy. And you can see this with gravity, for instance. Which direction does gravity push or pull? Gravity force is in what direction? Yeah, gravity is pulling in the downwards direction. But what happens to the potential energy of an object as it moves downwards? Yeah, as an object moves downwards, its gravitational potential energy decreases. So if we're going from if we have a high potential energy zone here and a low potential energy zone here, the force is pointing towards lower potential energy. That's a good way to think of what this negative signifies in both of these equations, really. That the negative sign signifies the force associated with that potential energy is pointing towards lower potential energy zone. So whatever is the direction of decreasing potential energy, that's the direction the natural force pushes or pulls. Any questions on that so far? So let's try actually applying this to gravity and springs, the two main examples we're going to be looking at here. If we're dealing with gravity, the force of gravity, the natural force that gravity applies to any object, is any idea how you would calculate how strong the force of gravity is? Like if you've got several objects, what determines how strong the force of gravity is? Why would they experience different forces from gravity? Like if I'm holding two objects, maybe they're different. The force isn't so much about position though. If I'm holding an object here, I have to apply a certain amount of force just to hold it in place. If it's higher up, I still have to apply the same force to hold it in place. But what if it's a different object? What could be different about another object that makes it easier to hold in place or easier to lift? The mass. The more massive it is, the stronger the force of gravity is. So force of gravity is proportional to mass. It's going to be mass times something. But remember, we want the units to work out. We've got kilograms, we want newtons. What sort of value do you have to multiply a mass by to turn it into a force? Force equals mass times what? Acceleration, exactly. And this is specifically going to be an acceleration we call the acceleration of gravity, usually written as g. And this literally just represents how fast an object would speed up if it's in free fall. If you've got a falling object, as it falls, it's getting faster and faster. G represents how quickly it's speeding up as it falls. And this varies depending on what planet you're talking about. If you're talking about Earth near sea level, acceleration of gravity is about 9.8 meters per second. 9.81, I think. Or if you just need a quick estimate, you can approximate that as about 10 meters per second squared. Generally, I would use 10 meters per second squared if you just need a quick calculation in your head without having to reach for a calculator, or if the problem specifically says assume 10 meters per second squared. If you need a more accurate value and you're going to be using a calculator anyway, I would use 9.8 to be more accurate. But really, if in a lot of the situations, they're going to be telling you assume gravity is about 10 meters per second squared, just to keep the calculation simpler. And of course, this varies from planet to planet. If you're talking about, so let's say, an object on the moon, G is going to be a much smaller value. I think it's about 1/6 as much as it is on Earth. On Mars, it's weaker than the moon, or weaker than Earth, but stronger than the moon. I think it's about 1/4 as much as Earth. And so it's going to be different from planet to planet. But if you're on the surface of the Earth, roughly near sea level, it's going to be pretty close to 9.8 meters per second squared. The higher up you are, the weaker it gets, but not by very much. Any questions on that so far? So let's try applying this idea of potential energy as an integral. If you are standing here, or let's say crouching, let's say you want to pick up a box. So you go from bending with your knees, not with your back, hold the box and pick it up. You are lifting up this object from some initial height to some final height. And you're applying a force that exactly counteracts the force of gravity as you do so. So we can calculate the amount of work. Instead of going back to the definition of work, we can use the general formula we just created. The change in potential energy should be the negative integral of force with respect to position. Although since we're lifting it vertically, we should be probably replacing x with what? What variable do we usually use for vertical motion? Yeah, so let's replace the x's with y's. It doesn't really matter what we call it. It's just going to be a little easier to understand, I think, if we use y instead of x. So let's write that out. Change in potential energy of gravity should be negative integral from y initial to y final of force of gravity integrated with respect to y. Oh, one other thing I forgot. Which direction is the force of gravity? Downwards. And usually we treat upwards as the positive direction. So we should really have a negative in our formula for force here. Fill that in. Force of gravity is negative mg. The negatives cancel out. Also, mg is a constant. The mass of the object doesn't change. The acceleration of gravity is just 9.8 meters per second squared near Earth. So if we pull out the mg and the negative from the integral, we just get mg times integral of 1 dy. And what's the integral of 1 dy? Integrate 1, and what do you get? Yeah, or in this case, y, since that's the variable of integration. the derivative would be 0, but the integral of a constant is just that constant times the variable in question. So we end up with m times g times y, but it's going to be y final minus y initial, so that'll be mg delta y. So that's potential energy of gravity. Change in potential energy of gravity is mass times gravity times change in height. Any questions on that so far? And one challenge I want to give you, try doing the same thing with a spring. For a spring, I'll give you the starting point that the force of the spring is negative k times x, where x is how far the spring is stretched or compressed, k is a constant representing how sturdy the spring is, and the negative sign is just because the force is in the opposite direction of x. If you stretch the spring to your right, you get a force to the left. If you compress the spring to your left, you get a force to the right. So try running through the same integral using this as the force and see what you get for potential energy of a spring. See if that integral result matches up with the formula they give you. Any other questions on that? All right, let me know by email if you have any other questions or if you want to request any topics for next time. Have a good weekend, and I will see you then. You're welcome.